In this presentation, we are going to introduce an interactive visualization tool that is used to demonstrate how convolution operations can incur foveation effect, and how the padding mechanism dictates these effects. Padding is a process of adding pixels around an image while being processed by the CNN. In addition to the input image, padding is usually applied at any convolution layers in CNN. Without paddings, the pixel information at the periphery of an image cannot be fully utilized after several layers of convolution operation. We refer to such uneven treatment of input pixels as foveation effects. These effects have strong influence on the CNN performance. When zero padding is applied, you can see that in the right side that the foveation effects are largely mitigated. This means the CNN can utilize more information at the periphery. We want to understand why these foveation effects emerge in CNNs. Moreover, there are several alternatives to standard zero padding, and we want to find out how foveation effects look like under different padding mechanisms. To understand these effects, we introduce an interactive visualization tool to demonstrate how these effects emerge in CNNs. This tool consists of several parts. On the left side, we show a list of padding strategies. Clicking on an item shows a brief introduction about the selecting padding strategy. In the middle, we show an example 2D input. Next to the input, we show the number of times each pixel is effectively utilized by convolution operations. The resulting heat map reveals the foveation effects under the selected padding strategy. Finally, at the bottom part, we show a detailed animation of how these numbers are computed, as well as interaction functions for step-by-step illustration. Now, let's take a look at these padding methods. The first padding strategy we are showing here is a valid padding, which is a case we do not apply any padding around. For a 3x3 kernel, if the pixel information can be fully utilized, like pixel M, we can see that it is utilized 9 times at different positions in the kernel. Here, we can actually stop the animation and go through 9 different convolution operations by ourselves. Different from pixel M, the information of pixel A, B, C, D cannot be fully utilized in convolution. You see pixel A is involved with the kernel once, for B twice, and for C 3 times. This heat map shows the number of times each pixel is utilized by the first convolution layer. After several convolution layers as shown on top, only a few pixels in the center can be effectively utilized by the neural network. Now, let's take a look at the zero padding, which adds just zeros around an image. For pixel A, instead of just utilized once, it can be utilized 4 times by the kernel, and pixel B is utilized 6 times in the first convolution layer. Zero padding can mitigate the foveation effect. And if you apply circular padding, things are quite different. It puts the first row to the padding at the bottom and the last row to the top. Meanwhile, it puts the first column at the very right-hand side and the last column at the beginning. Let's check pixel A again. The information of pixel A actually appears at all the 4 corners in the image, and it is similar to other pixels at the periphery. So all the pixels can be utilized equally. A mirror padding has a similar result. For its symmetric mirror strategy, it duplicates the pixel information next to the edge, and all the pixels are involved in the same number of convolution operations. Just to keep in mind, for the pixels at the periphery, the pixel information may repeatedly used by the same cell of the kernel. For example, pixel A is involved with the upper left corner of the kernel 4 times. The first time, second time, third time, the 4th time. Other padding methods can lead to foveation effects. You can explore that by yourself using our interactive web application. Some takeaways from this interactive visualization tool. First, valid padding, or no padding, results in strong foveation effects. Second, zero padding is common and effective. It helps mitigate these effects. Circular padding and mirror padding warrant each pixel is involved in the same number of convolutional operations, and other padding methods still lead to uneven pixel treatment. Thank you.